Good morning, it's Mrs. Hanson. I have made some changes on the assignment guide since these last couple topics are dealing with volume. Looking at some 3D images, we decided to separate the assignments into smaller assignments and to do shorter lessons over the next few days. So please make sure you're using the assignment guide that is posted on Canvas. Instead of having just days 3, 4, and 5 left, or 3, 4, 5, and 6, it goes, I think it was 3 through 5. It's going to go 3 through 8. Okay, so we've broken it up to, so we can work just a little bit each day over these. So over the next 4 days of e-learning, and maybe by that 4th day we'll be back in school, we are going to be looking at finding the volume of a solid. And the way we get that solid is you're going to have a region. In this picture here, it just shows a rectangle. And if you were to rotate that rectangle around the x-axis, you'd be left with that disc that's there. And that disc is just a right circular cylinder. And if you think back to geometry, how you found volume of a cylinder, it was base area times height. So obviously here, our base is a circle. So you get pi r squared, and then times the height of your cylinder, which in this case is width. Okay, so this is going to be something we're going to be using to help us find volume of these different figures. Okay, so our objective is to find the volume of a solid of revolution using the disk method. Okay, so today we're just going to be rotating around x and y axes. Tomorrow we'll be rotating around other vertical and horizontal axes, and then we'll get into the washer method, which is where you'll have a hole in the middle of that disc, so we don't want to count that as our volume. Okay, so let's take a look at what it'll look like if it's rotating around our x-axis versus our y-axis. Okay, so let's say we have our axes here, and let's say we have some curve, and it looks like this. Okay, and kind of picture like a sheet of paper. You're resting on top of the x-axis, and what we're going to do is we are going to rotate that around our x-axis. So picture that rectangle there. And when we do that, we are going to end up with a solid that we're going to go ahead and find the volume of. Okay, so picture this disc rotating around, or that rectangle, sorry. And that will be one of your discs. So off to the side, we can draw a picture of that disc and kind of picture the 3D image there. And the width of that disc, so when it's rotating around our x-axis, that's going to be our dx. This is going to be whatever your height of your rectangle is. That's going to be your radius of that disc. And what you want to picture here is a bunch of discs put together. Okay, so you're going to have discs over here, and obviously as you get to the highest point of the original curve, the larger the radius. okay? So as you get to the x-axis or the origin, or where this curve intersects the x-axis, the radius is going to be getting smaller. So if you think back to when we learned area under a curve, remember the more rectangles we could draw, the more accurate the area. Here, the more discs we can fit in, the more accurate the volume, okay? So what this is going to give us is that the volume of this figure is going to equal, so let's say it's starting at 0 on the x-axis and intersecting here at the letter B. It'll go from 0 to B, and we already reviewed that the volume of a cylinder is base area times height. So in this case, it's pi r squared. Your radius, I'm calling it our function r of x, because the radius is going to change. As you can see, the height of this curve, if you were to draw in rectangles to rotate around to do other discs, sometimes the rectangles are tall, sometimes they're really short, okay? So the height of that rectangle is going to be changing based on the x value of the function, and this will be, so pi r squared, and we are solving this in the direction of dx, okay, or in the x direction. So that will be our formula we will use to find the volume of this solid here, okay, by adding in a bunch of discs and their volumes together to kind of, so I'll shade this in so you can see that in the end this is all shaded and it is one big solid. Okay, so that's what it'll look like if it's rotated around the x-axis. Then what we're going to do is look at it, what it'll look like around the y-axis. Okay, so let's say we have this curve. This is the point 0, I'll say D. This is intersecting 0, 0, and I'll shade this in. So we have this. Again, you can picture a piece of paper here, and you're going to rotate it around the y-axis, and once you do that, what you're going to be left with is a solid, okay? So let's take a look at what this will look like. Because we're in the y direction, we're going around the y-axis, our triangle, or our rectangle, is going to be perpendicular to our y-axis. And what you want to do is picture that rectangle there, rotating around. It's easier to see, I think, in the y direction, to create this solid here. And you can see the height of that disc is the change in y, okay? So if we take and we draw this disc off to the side, your radius is no longer r of x, it'll be r of y, and the width of that disc will be your dy. So to write our volume here, it will be the integral from, since this one is starting at a y value of 0 to a y max of d, it's pi, your radius squared, and in this case we're in the direction of our y-axis, so we will have to be writing our equations in the form of x equals, so it's in terms of y, and that will go inside. Okay, so those are just the setups for the problems. I am going to pause this and do probably do 2 more videos for today. One where I'm explaining an actual problem going around the x-axis you trying one around the x-axis and then me explaining it. And then the third video for today will do them in the y direction, okay? Just so these videos don't get too long.